All right, greetings everyone. The purpose of this video is to go over an example of finding hydrostatic force on an object. Now, I'll say this is a more simple version um, of the types of problems you'll be doing, but I do think that it's a good example for getting down the basics of how to do these problems. So just like we had for pumping problems, we have a problem-solving strategy for finding hydrostatic force. So just like with the pumping problems, we always want to start by drawing a picture and selecting an appropriate frame of reference. Our second step is to figure out what are called the depth and the width functions. So basically functions that describe how deep a layer of water is and also how wide it is. Once we have those, we use this integration formula, which is this value rho times g times that depth function times that width function. And it says s of x, w of x, and dx, but this can really also be s of y, w of y, and dy, depending on the situation. Okay. And in this function, or in this formula, rho is the density of the liquid. Now, typically our liquid is going to be water, so we're going to use that 1,000 kilograms per meters cubed that we saw in pumping problems. And then g is always the force or acceleration due to gravity, which is 9.8 meters per second squared. Okay, so let's look at an example of this. So we've got another water trough. This time it's 12 meters long and has ends like inverted isosceles triangles, whose bases have length 6 and whose height is 4 meters. Now, I'm not going to show it here, but if you would like to, these slides are posted on WallMap, and you can follow the link to this video here to kind of see a little bit more about hydrostatic force or exactly what it looks like. Okay, so just like with the pumping problems, we're going to start by drawing a picture. So our trough, this time, we know that the ends look like inverted isosceles triangles, meaning isosceles triangles that are flipped upside down. And if you remember, isosceles triangles are triangles that have two sides the same. So in this picture, this side and this side would be the same. And the base length of this isosceles triangle is 6 meters. Its height is 4 meters. Okay, and then the trough itself is 12 meters long. So it's going to go out this way 12 meters. Now, in this case, I'll tell you right now that 12 meters actually ends up being not an important piece of information since we're just looking at the force on one end of the trough. Okay. That also helps us to build our reference here. Now, our frame of reference, or that's not the right word. No, it was the right word. Now, I'm going to do something that might seem a little strange at first, but I'm actually going to draw a separate picture over here for the frame of reference. And I'm actually going to take the end for this frame of reference. I'm going to take the end of the trough here, so this, and I'm going to flip it over. Okay. So I'm going to draw it now, not with that color though. Draw it so it looks like this. Okay. And hopefully it'll become clear in a minute why I did that. So I'm again going to label my distances here. So I know that the trough or the base of the isosceles triangle is still 6 meters long here, and the height is still 4 meters. Okay. Now let's look at finding the depth and the width functions. And similar to pumping problems, we want to think about if we have a layer of water here, right? The depth function is going to relate to, well, how far down is that level of water? And then the width function is how wide is it at a particular point. And they're called functions because they're functions of how deeper you are, more or less, right? Well, if I kind of superimpose the same layer over here, let's say it's right here, more or less, right? The depth function, which is, I'm going to call s of x, or actually s of something here. I'm not going to say what the variable is. Notice that the depth, in this point, the top of the trough is now on the bottom, right? So here was the top over here. That's become the bottom in the picture on the right. And the depth is going to be the distance below that it is, right? So this distance from here to here. Well, notice me having drawn the picture the way I have here, that depth is basically going to be whatever the y value is right there, right? If the depth was here, if it was up to here, well, the depth would be that y value. If it was here, it would be that y value. So drawing it like this makes our depth function, fortunately, fairly easy to figure out. So it's just whatever the y value is for that layer, which makes it a function of y. All right. Now our width function at that point, well, it's going to be however far off we go this way and this way. And notice that that corresponds, again, just kind of like in the pumping problems, it corresponds to some points on these functions here, which are out, or these lines here, I should say, which are out to some value of x, right? And because of symmetry, because this is a isosceles triangle, it's going to be the same on the left side. It's going to be out to a negative x value. But in both cases, we're going x units in each direction, right? So our width function here ends up being a function of x. It's this x in this direction, x in this direction. So it's x plus x, which is 2x. All right. Okay, so we've got those two. We can plug them into our formula. Before we do that, though, a couple things we need to figure out is with what we're going to, with respect to what are we going to integrate. And then also we have one of these functions in terms of x, one in terms of y. We need to figure that out. And sorry, I'm just redrawing some stuff here. Now, because kind of the width depends on where you are, the depth you're at, right? I think what I want to do is rewrite both of these functions in terms of the variable y, since it seems like the depth, the distance the water is below the surface, has a big influence here, which means we somehow need to get some sort of relationship between the variables x and y. Now to do that, note that this green line here, it's a part of the trough, but it's also, if I extended it, it's a line, right? And we know that for linear functions, we can find their equations. All we need are 2 points. We can find 2 points because notice that this one up here, we're told that that's a distance of 4 meters from the top to the bottom. So we know that that's the point 0, 4. This point here, well, we know that the entire distance across the top of the trough, or the base of the triangle, is 6 meters, which means half of it, this distance right here, would be 3 meters, which tells us that this point right here is going to be the point not 0, 3, but 3, 0. Okay, so we've got 2 points on the line. We can use our general form for a line, which is y equals mx plus b. Again, I'm not going to go through all the details here. I'll leave that to you. When we do that, we end up getting that the equation of our line in this case is, it's here somewhere in my notes, is negative 4/3 x plus 4. But we need to get x in terms of y for our width function over here. So I can do some algebra. Again, I'll leave it to you to check this. But when I do that, we end up with this being x equals negative 3/4 y plus 6. Or sorry, plus 3. Okay. All right, give me just 1 second here. Okay, so we can plug that in for the width function over here. Apologize that I'm running out of space. We're now going to have our width function with respect to y, so it'll be 2 times that value for x, which is negative 3/4 y. Negative 3/4 y plus 3. You can distribute the 2 there. And when we do that, oh my lord, sorry. Oh my gosh. I don't know why my pen is being weird here. There we go. We end up with negative 3/2 y plus 6. Okay, so now we have both our width and our depth functions in terms of the variable y, and I apologize, it's gotten so sloppy. So I'm going to go to the next slide here. And now that we have that information, we can go ahead and plug it into our formula, which is rho times the value of g times our depth function times our width function. And again, because everything's in terms of y, we're going to integrate with respect to y. So we plug everything in. So that value rho, remember, is 1,000 kilograms per meters cubed. The value g, the gravity constant, is 9.8. Our width function, or sorry, our depth function was the value y. And then our width function, negative 3/2 y plus 6 dy. And we can do some simplifying here. We can multiply these together, but they're also a constant, so we can move that out to the front. We can distribute the y here. And so when we do that, we end up with our integral becoming 9,800 times the integral of negative 3/2 y squared plus 6y, and we distribute that y up above. And just like with the pumping problems, the thing we have left to figure out are our bounds. Okay. So to figure out the bounds, we'll go back here to the picture, which I know is super sloppy now, but we're integrating with respect to y, so we just need to think about what y values are we covering, and we're going from here up to here. So it looks like we start down at 0 on the y-axis because the height of the trough of the triangle is 4 meters. It goes up to 4. So our bounds of integration here would be from 0 to 4. Okay. Then we could work that out. And again, I'm going to leave the details to you to check. But when we do that, we end up getting 156,800. And our units here would be newtons, since we're working in the metric system here. All right, that's it for now. Thank you for watching.